Good morning, everyone. Myself, Dr. Amit Shrivastava. I'm professor in CSE department, SIRT Bhopal. Continuing our previous lecture on memory management. So this is the lecture 2 of module 2. Here we will be discussing various topics like swapping, multiple partitioning scheme, external and internal fragmentation, paging, introduction. So swapping, a process can be swapped temporarily out of memory to a backing store and then brought back into the memory for continued execution. What is a backing store? It can be any fast hard disk, which is large enough to accommodate copies of all the memory images for all the users. Swap out, also known as rollout. So program is temporarily swapped out from the main memory to the backing store or the hard disk. And swapping or rolling means program is swapped in from backing store or hard disk to the main memory for continued execution. Major part of swap time is the transfer time. So total time transfer time is directly proportional to the amount of memory swapped. So this is how we do. This is our operating system, and here our process are executing in this memory space, which is a user space. So whenever the process finishes its time slice, then we can swap out that process into the hard disk, and a new process can be brought in or swapped in into the user space for execution. And then when again this process time slice is over, this will be again swapped out and the older process can be swapped in. And so this is how we can manage the memory, smaller memory for larger sized programs. Okay, so now let us discuss how much time is required. So context switch time, which is the total time which we require for transfer the data from the RAM into the hard disk and vice versa. So let us say a user process is of size 10 MB. Transfer speed of hard disk is 40 MB per second and rotational latency time is 8 milliseconds. Head seek time is not given, so we can ignore that time. So what will be the swap out time? The swap out time consists of 3 different types of times: head seek time, rotational latency time, and transfer time. So transfer time will be total memory of the process, total space of the process is 10 MB, and the transfer speed is 40 MB per second. So 10 upon 40, that gives us 1/4 second or 250 milliseconds. So swap out time will be head seek plus rotational latency plus transfer time. We have not been given head seek time, so we can ignore that time. So rotational latency time is 8 milliseconds and the transfer time is 250. So 258 milliseconds will be the swap in time. So swap out time and swap in time will be equal, obviously. So total swap time for one process which we require is 516 milliseconds. So if we are using the round robin algorithm, then time slice should be much greater than 516 milliseconds, so as to effectively maintain this particular process. Otherwise, if the time slice is less or equal to 516 milliseconds, then in that case, the efficiency of the system will automatically be 50% only, because for 516 milliseconds, we will be executing the process if the time slice is 516 milliseconds, and 516 milliseconds will be required for swapping out and swapping in. So the system efficiency automatically decreases to 50%. So the time slice should be much greater than this 516 milliseconds. Okay. Now, hardware support for the relocation and limit register. So suppose this is our CPU, which is generating one logical address. Now this logical address is compared with the limit register. Limit register is holding the total length of the program. Like suppose if I have my program size, a program is 500 statements long. So the logical address should be anywhere between 1 to 500. It cannot be more than 500. So we check this logical address whether So limit register will be holding 500 because the size of the program is 500. So logical address should be less than 500. If it is not, then we will trap it because it is an addressing error. If it qualifies this test, yes, then we go further and we add the relocation register as we have already discussed in the previous topic. So relocation register will be added to that logical address to get the physical address. Okay. So next is contiguous memory allocation and multiple partition allocation we will be discussing. So first of all, see what is a hole. Hole is nothing but a block of available memory. Holes of various sizes are scattered throughout the memory. So when a process arrives, it is allocated memory from a hole large enough to accommodate it. Operating system maintains information about the allocated partitions and the free partitions, which we are calling the hole. So suppose this is the scenario, operating system, and we have got three processes here, process 2, 5 and 8. After some time, this process 8 finishes its execution. So we are left with free memory here. This is what we are calling the hole. Let us say after some time, process 9 comes and it doesn't require the complete memory. So whatever memory we process 9 is requiring, we will allocate this from this free memory or from this hole. So again, process 9 is allocated the memory and this remaining memory is again a hole. Again, process 10 comes, so it will be allocated the memory from this hole, and after giving the memory to the process 10, whatever memory is left, this is again we will call the hole. So this allocated partitions and free partitions or holes are maintained in a table by the operating system. Now, dynamic storage allocation problem. So how to satisfy a request of size n from a list of free holes? So suppose we have got a list of free holes. So which hole is to be allocated? So we can make use of three different schemes for that. First fit algorithm, best fit and worst fit. First fit algorithm says that allocate the first hole to the new process. The hole should be large enough or big enough to accommodate that process. It means if the process size is, let us say, 10 KB and the hole size is 15 KB. So it is large enough to hold that process. So we will allocate that 10 KB from this 15 KB. Okay. Best fit means to allocate the smallest hole that is big enough, and it must search entire list unless ordered by size. Because if we want to find that hole which is large enough to accommodate the process, but it should be the smallest hole also. So, for example, suppose I have got three holes of different sizes. Let us say first hole is of size 10 KB, second hole is of size 20 KB, and third hole is of size 30 KB. Let us say the process comes which requires 15 KB of size. So 10 KB hole cannot accommodate that 15 KB process. 20 KB and 30 KB, both the holes can accommodate that 15 KB process. But which hole we will be allocating? The smallest hole which can accommodate the process. So in this case, the 15 KB process will be allocated the hole of size 20 KB, because this is the smallest hole which is large enough to hold that process. So for this particular best fit algorithm, I will require to search the complete list of holes, right? It produces the smallest leftover hole. Worst fit is the opposite of best fit. It allocates the largest hole. Again, for this also, I will have to search the entire list. So what is the benefit of worst fit, and what is the disadvantage of best fit? So worst fit advantage is that if we accommodate largest hole, let us say, let us discuss again the previous example. I've got the hole of size 10 KB, 20 KB and 30 KB. Process size is 15 KB. If I accommodate in best fit, I will be allocating the 20 KB hole. So I'm left with only 5 KB memory, right? Out of 20 KB after allocating that 15 KB to the process. So this 5 KB may not be large enough to accommodate any other process. But if I make use of this worst fit algorithm, it will accommodate the largest hole. So I will allocate 30 KB size 30 KB hole to this 15 KB process. So I will be left with 15 KB of free space from this hole, and this 15 KB can be large enough to hold another process. So this is the benefit of worst fit, and this is the disadvantage of best fit. Okay. Now, first fit and best fit are known to be better than the worst fit in terms of speed and storage utilization. Now, fragmentation. So there are two types of fragmentation: external fragmentation and the internal fragmentation. So external fragmentation is the total memory space exists to satisfy a request, but it is not contiguous. It means throughout the memory, physical memory, different memory spaces are left, but they are not large enough to accommodate any process. Then we will call that it is an external fragmentation. I will explain shortly with the help of the diagram. Internal fragmentation means the allocated memory may be slightly larger than the requested memory. This size difference is memory internal to the partition, but not being used. We can reduce the, again I will explain this with the help of the diagram. We can reduce the external fragmentation by the compaction technique. Okay, so first of all, let us look at this diagram. So I've got these 1, 2, 3, 4, 5. 5 processes are at present in the main memory, and their sizes are also mentioned. Segment 4 is requiring 7K of space, segment 3 is requiring 8K of space, and so on. After some time, let us assume this segment 1 finishes its execution. So this 8K of space will be freed up. Okay, so here 8K of space is freed up. A new process, a new segment 7 comes, which requires only 5K of space. So out of this 8K, we will give this 5K to this segment 7, and we are left with this 3K. So this is our whole, right? After some time, this segment 4 also finishes its execution. So 7K of space will be freed up. A new process, segment 5 comes, which requires 4K of space. So out of this 7K, we will give this 4K. So we are left with this 3K. So we are left here also with 3K of space. This is again a 3K of space. So two holes are at present we are having in this memory. Now what happens? Total space, total free space which is available at present is 6K. If a new process comes which requires 5K of space, then I cannot give that 5K of space to that process because the contiguous memory space is not available. And that is why we say that this is an external fragmentation. Because of this 3K and 3K, it was available at one place only. So total 6K of space was available at present. But since it is scattered, so we are not able to accommodate the 5K of process here, right? So again, see this diagram. So here segment 3 is finished. So it will release 8K of space, and segment 6 comes, which requires 4K. So again, we are left with 4K. So now at present, we have got 4K, 3K, and 3K. That is total 10K of space is available, but this is scattered. So what compaction technique does is it shift all the free memory to one place and all the used memory to the opposite side. So here we have done this only. So this 10K of space is now contiguously available with us. So if any process of 9K comes, then we can accommodate this with the help of this 10K of hole. But it was not possible before applying this compaction technique. Here it was not possible. So this scattered free memory is known as external fragmentation. Now what is internal fragmentation? So let us assume that a new process comes. We are here, right? We are at this place, and a new process comes which requires 3K minus 1 byte. Okay, so 1 byte less than this 3K. So what we are going to do, we will allocate that process this complete 3K of memory. Why? Because if we allocate only 3K minus 1 byte to that new process, so we will be left with only 1 byte in this, and it will be treated as a whole. So this 1 byte is of no use for us. It cannot accommodate any other process. So what we do to avoid all this complexity, we will simply allocate this 3K to the new process. So this 1 byte, which is available in the process, which will never be utilized by that process, this becomes the internal fragmentation for that process, because we are accommodating, we are allotting the larger size memory to the process, which will never be utilized by that process. So this will be internal fragmentation for that process. Okay, this concept I have already explained about internal fragmentation. Okay, so this will require a little bit more time. So we'll end this lecture here itself, and we'll be discussing the paging scheme in the next lecture. Okay, thank you.